Hello everyone, welcome back to my VLSI diary. My name is Shivangi Upadhyay and today we are going to explore one of the most critical topic in RTL design, FPGA implementation and ASIC development, which is timing constraints. Imagine this situation, your RTL design is functionally correct, your simulation passes perfectly, everything looks good in the waveform. But when you run synthesis or implement the design on an FPGA, it fails. Why does this happen? In most cases, the reason is timing violation. And that's exactly where timing constraints come into the picture. Timing constraints tells the synthesis and place and route tools how fast your design should run and how signal must behave with respect to the clock. Without proper timing constraints, the tools don't know the timing requirements of your design. And that means even a perfectly written RTL design can fail on real hardware. So, in this video, we are going to understand what timing constraints are, why they are essential in digital design, and how they ensure that your RTL actually works reliably on silicon. Because in modern VLSI and FPGA design, writing RTL code is only half the job. Meeting timing constraints is what makes the design truly hardware ready. Now, let's understand what timing constraints are and why they are important in digital design. Timing constraints are basically rules or specifications that defines the timing requirement of a digital circuit. When we design a system in RTL, the code only describes the functional behavior of a circuit. However, the design also needs to meet certain timing requirements to operate correctly in real hardware. These timing requirements are provided to the synthesis and implementation tools in the form of timing constraints. The tool use these constraints to optimize the placement, routing, and logic implementation so that the circuit meets the required performance. Timing constraints typically specify several important parameters. First is the clock frequency, which tells the tool how fast the circuit is expected to run. Second is the data arrival time and required time, which defines when signal should reach different parts of the circuit. Third are the step setup and hold requirement, which ensures that the data is captured correctly by flip-flops related to the clock edge. And finally, we also define input and output timing, which specifies the timing relationship between external signal and the internal clock of the design. Once these constraints are applied, the tool performs static timing analysis or STA. STA check whether all the timing paths in the design satisfy the required constraint and verify if the design will work correctly at the target clock speed. So, in summary, timing constraints help convert a functional RTL design into a timing correct hardware implementation. Let's understand why timing constraints are important in digital design. When we design a digital circuit using RTL, the main focus is usually on functional correctness. This means we ensure that the logic performs the intended operation or not. However, in real hardware system, it is not enough for a design to simplify work logically. It must also operate within specific timing limits. This is where timing constraints play a very important role. Timing constraints provide the synthesis and implementation tools with information about how fast the circuit should operate and how signals must propagate through the design. One of the main reason timing constraints are important is that they ensure the design meets the required clock frequency. Every digital system operates using a clock signal, and each clock cycle has a limited amount of time for data to travel through the logic. Timing constraints inform the design tool about the target clock frequency, allowing them to optimize the logic placement and routing so that all operations complete within the required clock period. Another important reason is that timing constraints help prevent setup and hold violations. As we discussed earlier, flip-flop require data to be stable both before and after the clock edge. If data arrives too late, a setup violation occurs, and if data changes too quickly after the clock edge, a hold violation occurs. Timing constraints help the tool analyze these conditions and ensure that all the data paths meet the required setup and hold timing requirements. Finally, timing constraints help ensure correct hardware behavior. Even if a design works perfectly in simulation, it may fail in real hardware if timing requirements are not satisfied. By applying the correct constraints, the design tool can perform static timing analysis and verify that the circuit will operate reliably when implemented on FPGA or ASIC hardware. So, in summary, timing constraints are essential because they help the design meet the required speed, prevent timing violation, and ensure that the circuit behaves correctly when implemented in real hardware. Let's discuss setup and hold constraints, which are two of the most important timing requirements in synchronous digital circuit. In a synchronous design, data is typically transferred between flip-flop using a clock signal. For the data to be captured correctly by a flip-flop, certain timing conditions must be satisfied. These conditions are known as the setup constraints and the hold constraints. For any timing path to operate correctly, both of these constraints must be satisfied. First, let's talk about the setup constraint. The setup constraint specifies that data must arrive at the input of the flip-flop before the active clock edge occurs. This means the data should be stable for a short period of time before the clock edge so that the flip-flop can reliably capture it. If the data arrives too late, meaning it changes very close to the clock edge, the flip-flop may not be able to correctly determine whether the data is a logic 0 or a logic 1. This results in a setup timing violation. Now, let's look at the hold constraint. The hold constraint specifies that data must remain stable for a short time after the clock edge. Even after the clock edge has occurred, the flip-flop still needs a small amount of time to properly latch the data. If the data changes immediately after the clock edge, the flip-flop may capture an incorrect value. This situation is called a hold timing violation. So essentially, the data must remain stable both before and after the clock edge to ensure correct operation. If either the setup constraint or the hold constraint is violated, the circuit may experience timing errors. In some cases, the flip-flop may even enter a state called meta-stability, where its output becomes unpredictable for a short period of time. This is why, during static timing analysis, tools carefully check all the paths in the design to ensure that both setup and hold constraints are satisfied. So, in summary, setup ensures that the data arrives early enough before the clock edge, and hold ensures that the data remains stable long enough after the clock edge for reliable data capture. Now that we have applied timing constraint to the design, the next step is static timing analysis, commonly known as STA. STA is a technique which used by the synthesis and implementation tools to verify whether the design meets all the timing requirements. Unlike functional simulation, STA does not simulate the design with input vectors. Instead, it analyzes the timing behavior of the circuit mathematically by examining all possible timing paths. In STA, the tool checks every timing path in the design, typically from one flip-flop to another flip-flop, from input to flip-flop, or from flip-flop to output. For each of these paths, the tool calculates how long it takes for a signal to propagate through a combinational logic and routing. During this analysis, STA verifies several important timing parameters. First, it checks setup timing. This ensures that the data arrives at the destination flip-flop before the required clock age so that it can be captured correctly. Second, it checks hold timing. This ensures that data remains stable for a short time after the clock age, preventing incorrect data capture. SGA also analyzes clock skew, which is the difference in arrival time of the clock signal at different flip-flop in the design. Excessive clock skew can affect setup and hold timing and may cause timing violations. Another important factor analyzed is the combinational path delay. This refers to the total delay introduced by logic gates and routing elements between a sequential element. After evaluating all these parameters, SGA determines whether the design meets the required timing constraints. If all paths satisfy the timing requirements, the design is considered timing clean, meaning it can operate reliably at a specified clock frequency. However, if any path fails to meet the setup and hold requirements, the tool reports timing violations. These violations must be fixed through design optimization, logic restructuring, or placement and routing improvements. So, in summary, static timing analysis ensures that the digital design will operate correctly at the target clock speed before it is implemented in the hardware. Let's discuss the real world importance of timing constraints and why they are critical in practical digital system design. Timing constraints are essential because they ensure that a digital circuit operates reliably and correctly in real hardware system. When we write RTL code, we mainly describe the functional behavior of the circuit. However, in real hardware, signal must also meet strict timing requirements so that data can move correctly through the system. This is where timing constraints become extremely important. They provide the tools with precise information about clock timing, data arrival, and signal propagation, allowing the design to meet the required performance target. Timing constraints are widely used in several real-world applications, like in FPGA implementation. Timing constraints ensure that the design can operate at the desired clock frequency. For example, if an FPGA design is expected to run at 100 MHz, the timing constraints help the synthesis and implementation tools optimize the logic and routing so that all operations complete within a required clock period. Second, timing constraints are very important in ASIC design. In ASICs, designers must meet strict performance, power, and area requirements. Proper timing constraints allow the design tools to optimize the circuit so that it can achieve the required speed while maintaining efficiency. Another important application is in high-speed processors. Modern processors operate at very high frequencies, often in the gigahertz range. At such high speeds, every very small timing error can cause incorrect data transfer or system instability. Timing constraints ensure that all internal data paths meet the required timing so a processor operates reliably. Timing constraints are also crucial in communication systems. In these systems, data is transmitted and received continuously between different components. Correct timing ensures that the data is synchronized with the clock, preventing transmission error and ensuring accurate communication. So, the key insight here is that writing a code uh, of design is only the part of the design process. Even if the RTL logic works perfectly in simulation, the design may still fail in the hardware if the timing requirements are not satisfied. Therefore, applying the correct timing constraint in what ensures that the design actually works on real silicon or FPGA hardware. In simple terms, timing constraints help convert a functionally correct RTL design into a reliable hardware implementation. Thank you for watching this video. I hope this explanation helped you understand the importance of timing constraints in digital design. If you found this video helpful, feel free to like, share, and subscribe to my VLSI diary for more content on VLSI, FPGA design, and digital electronics. Thank you and see you in the next video.